Greetings everyone, this is non-expert here, back again with another video. Today we are going to be solving problem number 37 and difficulty has been rated at is easy. This problem was asked by Google and I've seen it being asked in Amazon and Microsoft as well. Alright, so the problem description is that the power set of a set is a set of all its subsets. So write a function that given a set, we generate its power set. Again, if you don't know what a power set is, it's basically all combinations that you can make from the elements which have been given to you, and just return those. So for example, if you're given the set 1, 2, 3, it should return an empty set 1, 2, 3, 1, 2, 1, 3, 2, 3, and 1, 2, 3. Basically all parents that you can make. Alright, cool. So fortunately we were able to find a similar problem on LeetCode, and the name of the problem is called subsets. Again, you can pause this video and check out the link given in the description below and try solving this on your own. But basically there are two particular ways of solving this particular question. The first way is to use recursion, or rather to be more specific, to use a DFS approach, and the other way is by using bit manipulation. So today we're going to be using recursion, and in the next video we're going to try solving this through bit manipulation, because both those solutions are pretty efficient, and let's just get down to it. What we want to do is we want to use DFS. So if you're not aware of what DFS is, let's just write these things down, that we're going to use recursion and DFS. And basically what we're going to do is we're going to go through all the paths that we can formulate using an index, and whatever paths that we presently add, all those paths are basically going to justify that that's the subset that we want. Again, if you sort of look at it as, you have 1, 2, 3 given over here, um, and you have an empty path to begin with. The way you're going to go about it is you're going to push 1 inside one path, then 2 inside another, and 3 inside another path. Then inside 1 you're going to push in 2 and 3, and then go forward from this. So basically you can represent it like this. Again, this is not the best depiction for this. Let me just check this out. Yep. So basically what you're doing over here is that you have 1, you have 2 and 3. Basically you've iterated through all the elements and you've pushed them down inside your path, and basically the path that you presently add, you're going to go through the index and then you're going to pass through all the other elements as well. So if you're at 1, then 2 and 3 are left, so you're going to put 1 and 2, and then you're going to make another path 1, 3, and for 2 you're going to make 2, 3, and 3 would not have anything as such, because there's no index afterwards. So, and with 1, 2, there's one more index which can be traversed, and that's going to be the last element. So 1, 2, 3 is the one that we need. So basically, in a way that you can see that all the paths that we've gone through are all the sets, all the possible sets that we need, and that's basically it. That's what we want to do in our approach as well. So before we start, we start with our base conditions. Our base condition is that if there are no numbers given, then we return an empty list. The other thing that we want to do is we have a result list in which we're going to store all our results, and we're going to make a DFS function. So we're going to have a DFS function over here, which is going to have a few things like the numbers, an index which is going to be 0, the path that we've traversed so far, and the result that we have. And eventually what we're going to do is we're going to return the result. And let's just talk a little bit about what I'm doing with the signature of the function. By the signature of the function, what I mean is y is nums and 0 and the path and so on given over here. So numbers is for obvious reason, we need the reference of all the numbers. The index is sort of going to help us understand like what all elements have we already traversed, and the path is something that we're going to always store inside our result. Again, if you did not know, Python uses pass by reference, which is very, very important for you to understand. So whatever operations that you're doing inside result, inside the DFS function, those things are going to be affected inside the result that you've declared over here. So that's something that we need. So if we do result.append, right, and we append the path, that's what we discussed before, those things are going to get appended inside this result, and whenever we return that, we're going to return the exact result. But due to this also poses a problem. The path by reference poses a problem for us, because the path that we have to sort of make sure that we're creating a new path or a new reference, because we don't want to have the same path over and over again. As in, if we if we keep on appending the same path, we're just going to have duplicates over and over again, right? And we need all the unique paths that we've traversed so far. Cool. So all you have to do is basically use the same DFS approach that is, pretty nominal. So the way we're going to go about it is that we're going to iterate from the index that we, traverse at till the last elements that we have. So till length nums. And all we want to do is we just want to recursively call our DFS function, and while you're doing that, the parameters that we're going to pass in is going to be I plus 1, because I plus 1. The reason for that is because you're going to obviously be traversed through the index, and we just update our path. And the way we're going to do that is we're going to use concatenation, and what this does for us is basically it makes a new list altogether, so the reference also sort of gets changed. So we handle the pass by reference issue as well, and that's basically it. So you've passed in nums, you've passed in I plus 1, you've passed in the path, and whatever element that you will presently add. So that gets your path and the result as well. And it keeps on getting appended, and eventually you return the result. And that's basically it. We can try running this. Hopefully this should run fine. Again, you can see that the sequence is sort of different than the output and the expected output, but the sequence really does not matter. So you can see 1, then 1 comma 2, then 1 comma 2 comma 3 gets printed out, then 1 comma 3. It's just basically the entire thing which I was showing you before. And cool, let's just submit this. Hopefully this should run. And as you can see, it's actually pretty fast. It's 97% faster than all the Python solutions which were submitted, and memory wise it's also pretty optimal. And again, the reason for that is just that you're using a simple DFS approach, where you're just iterating through all the indexes that you've gone through, and then just recursively calling your DFS call. Cool. So that's it for this particular approach. In the next video, we'll be going through the iterative bit manipulation approach. Both of them have their own justifications, and you can use both of them in the interview as well. But that's basically it. Again, if you did have any comments, you can leave it in the comment section below. And if you did like this video, do give a like and do subscribe to our channel. We are discussion over here, and we would love to have you. Again, if you've already subscribed, you're awesome. We all know it, and have a great day.